of code compared to the multi-core CPUs. So the fact that they did G80 and put in enough of the SMs to be able to get to close to a teraflop, somewhere around the 500 gigaflops, was absolutely essential for people to have the incentive to parallelize. So in terms of encouraging people to parallelize, that whole history was done pretty correctly. What they didn't do correctly, in my opinion, is that if you look at the kind of the programming model for CUDA, we pushed the low-level programming model to the application teams way too early. And you know what? It's by necessity whenever the industry does this, because they need to get customers, they need to get use cases. But honestly, after working with the industry team for close to 10 years now, even with writing a textbook and teaching classes and so on, I would say less than 10% of the application developers should be really exposed to these kind of the complexity. And we really expose way too much complexity to those teams, unfortunately. Yes. Owner, it's your job to cut me off. Okay.
Yes. So let's keep it short instead.
Yes. This is Kemal, Global Supercomputing. Now, you showed this example of deep learning getting better results than experts. In that case, really the final algorithm that is learned is seeing an image and quickly coming up, this is a cat, this is a dog, this is not a tank, this is a tank. But in normal artificial intelligence computing, the end result must usually be a deep combinatorial search. For example, chess playing requires heuristic search.
Yes.
That's an enormous scale. In my own work, in the Bach chorale program, there is combinatorial search.
Absolutely.
And combinatorial heuristic search. In the Doug Lennox automated mathematician, there are examples where you try heuristically and they were able to come up with Goldbach's conjecture through heuristic search. And so basically, there is a discrepancy between the deep learning methods and what they obtain at the end, which is a shallow algorithm.
Yes.
And the actual expert system results where the final result is a deep combinatorial search taking exponential amount of time. So how do you think that we can get closer to true artificial intelligence activities involving deep combinatorial search?
Yes.
And how do you account for the discrepancy between the
Yes.
deep learning approaches and what true difficult artificial intelligence tasks require?
Very good. So Kemal, for those of you who don't know the history, when I graduated in 1987, I interviewed at IBM, and Kemal was one of the giants who interviewed me. And he actually gave me my first job offer, by the way. So 30 years later, I'm here, and Kemal's asking the single most fundamental question that people have asked me for a long, long time. So let me approach it a little bit, just kind of, let me take 2 minutes to answer this question, because this is a very important question. The current deep learning and neural net-based approach is what I call the combinational logic equivalent of artificial intelligence. So basically, for those of you who are familiar with combinational logic, you have a truth table, and then you produce some kind of optimized, the logic or unoptimized logic, depending on the technology. That whenever you have an input, you produce an output. You have an input, you produce output. You have a picture. Here's a cat. You have a sound. Oh, that's Wen-mei Hwu speaking. So that's kind of the simple combinational logic formulation of AI, in my opinion. And what you mentioned, in my opinion, is the sequential logic equivalent of AI. That is, many of these real search algorithms cannot be easily formulated as a truth table-based single-step approach, and which, by the way, I believe the neural net approach is a combinational logic approximator. Essentially, if you think about that analogy, the logic, the truth table for the particular recognition logic is not clear. We don't know what the truth table should be. And we don't even know how many variables there should, input variables and so on there should be. So neural net is actually producing the equivalent of a truth table that, that many people actually don't quite know exactly what the numbers are, but they mimic some sort of truth table-based logic that give you some answer. So going back to the sequential logic, the analogy, the biggest problem that at least I'm seeing for getting into these kind of combinatorial search space and being able to have a reliable solution is, the state transition equivalent in those are actually extremely large. So there has to be some kind of heuristic approach to determine the most promising state transition in in that process. And that problem has been studied for decades. But this should be sound familiar to you. We study these problems for decades and we haven't got a really good solution. But for those of us who have been doing sequential circuit design, we know that the sequential circuit design, the state transition, is a combinational logic. So we could use machine learning to come up with some good heuristics in terms of the state transitioning for that search space. And I actually think that that's a very fruitful area that people have not paid enough attention as a research topic. Now that you ask. Thank you.
Let's thank Wen-mei.
All right, thank you.
The next session will be